In this lecture, we're going to begin by taking a look at the energy balance for fluid flow in a pipe. And so this is a pipe with either a constant surface temperature that is different from the fluid or with a constant heat flux. But in any case, there's heat transfer on the surface. So I'll begin by drawing out a schematic of a pipe, and then we'll apply an energy balance to that pipe. Okay, so here is a schematic of our pipe, and what we have is we have a pipe with fluid coming from the left to the right. The fluid begins at the inlet I, and then eventually at x equals L, it goes to the outlet O. But what we're going to do, we're going to consider a section of the pipe in the middle where we have heat transfer taking place. And so we're going to say that we have convective heat transfer coming in. And we don't know the exact nature of that, but we do know that it is through convection. So it could either be constant temperature, constant heat flux, or a combination for right now. But the way that we will quantify that is we are going to have some surface heat flux in watts per meter squared. And then we're going to multiply it by the area, or the wetted area on the inside of the pipe. And that is going to be the perimeter of the pipe multiplied by dx. And dx is the length of our little differential element that we are applying the control surface to. So we have fluid coming in at a bulk temperature Tm and leaving at a different temperature. So it's either becoming hotter or cooler, but there is a dTm. And then we also have the pressure multiplied by nu. That is the specific volume. And then on exit, we have the pressure times specific volume plus the differential change of the PV term. So to express that, what we have is TB, that's the bulk temperature, mixing cup temperature. It is also equal to Tm. And so that is the bulk or mean temperature. And the other thing that we have is nu, and if you remember from thermodynamics, that's where we use specific volume quite often. It is 1 over the density, and so that is specific volume. All right, so that is the system that we are going to perform an energy balance on. We're going to perform an energy balance on the control surface. So let's go ahead and start that process. So to begin with, remember we said that we have some form of convective heat transfer around the perimeter. So energy is coming in that way. And then we have energy flowing into our system on this side because we have flow coming in here. So energy is flowing in. And at the same time, we have energy flowing out through the fluid. And all of this needs to equal 0 because we're operating in a steady state. And if you're wondering where I'm getting these terms from, essentially this is just the first law of thermodynamics, and the CVT, that is our internal energy. PV is the flow work because we have an open system where we have mass crossing our control boundary. And so that is where that formulation is coming from. But now with this expression, what we note is, first of all, some of the terms are going to cancel out quite quickly. Most importantly, this and this cancel out. And then what we're left with for the differential amount of heat being transferred through convection is equal to the mass flow rate times the following. And we have that expression there. Now, what we're going to do, we're going to work with expressing this and this in other forms. And we're going to take advantage, we could have a liquid or a gas, but let's consider if we have a gas for right now. So we know through the ideal gas equation, we have that expression, and here that is the relationship between C sub P and C sub V. And so what we can do, we can make a substitution here. First of all, for the PV term, and then noting this, the CV plus R, that is just CP TM, and consequently we can rewrite Q convection as being the following. So that becomes one expression that we can work with, and we will be working with that as we go through. Now, if we're dealing with a liquid, and so what this is saying is that if we had been dealing with a liquid, the specific volume of a liquid is very small. And for a liquid, Cp is equal to Cv, and consequently we would result in the same equation for a liquid. So although we made the assumption of the ideal gas, it equally we could have gone through for a liquid and have come up with the same. So that means that this expression here applies for both a liquid and a gas, which is good because that's what we'll be using it for. Now, what we can do, we can take that differential equation and we can integrate from the inlet to the exit. And we obtain this expression, and I'm going to box it because we will be using this expression later on in this lecture. And the last thing we can say is we can look at Fourier's law. And if all of the heat is being transferred along the inside wall of the pipe, we can write out Fourier's law in this manner. Now, this here, that T wall, that could also be expressed as T surface. And then this is the fluid temperature, Tm, or the bulk fluid temperature. So this is what we have been looking at. We've been finding ways of obtaining this, and quite often we have relationships for Nusselt number for either laminar or turbulent flow, and we can determine the value of H. But the thing that we now need to ask is, how can we handle this temperature difference for different types of problems? And what I'm referring to is that if we have a constant wall temperature, for example, how is the bulk temperature going to vary as a function of position along the pipe? And if we have constant heat flux, how will this vary as a function of position along the pipe? And so consequently, we have a bit of a challenge when we're dealing with pipe flow in terms of being able to resolve this term here. And that is what we are going to be looking at in this lecture, finding a way or ways to be able to handle the temperature differential term for convective heat transfer in pipe flow. So that's where we'll be going in the next couple of segments.